Hello, here we go with Chapter 3, Lesson 3. The author starts with a cartoon. Took me a while to actually figure out what's going on here, but let's have another smiling contest. So they're smiling at this guy as he walks around, and there you can see some teeth. So it's kind of weird. That's why the 360-degree smile. Maybe you can figure out why he used this one. We're going to be talking about degree measures and protractors and circles. Before we get there, a mind trap. Think about it, see if you can figure it out. We'll talk about it in class if I can remember. So here we go, protractor and angle measure. And what's really going to help you is if you recall, look back at what we did with the ruler postulate. If you recall last lesson, we talked about how the ruler postulate works. The points on a line can be numbered so that positive number differences measure distances. And then we defined what puts a point between two other points on a line. You recall we said if its coordinate is between their coordinates. And then finally we said if a point is between two other points, we know that if you add the two segments together, you're going to get the length of the entire segment. So all dealing with distances with the ruler postulate. Today we're going to be talking about a protractor and a new postulate, the protractor postulate. So what is that? Yeah, it is a ray. You are correct. It's got one endpoint and goes on forever in the other direction. Now what is it? Well, it's still a ray. It looks like it just went around in a circle. Here's another picture. This is a type of protractor that's kind of nice. It's kind of nice because instead of just going to 180 and having two different scales you'd have to guess at, here you can see that this protractor starts at 0 and goes all the way around and ends up at 55, 6, 7, 8, 9, 360 degrees. So what we actually call that ray that we just saw, it's a ray traveling through a full rotation, which again then would be 360 degrees. We have another ray here, and maybe you can guess. That is a ray that has done what? Yes, there's our normal protractor, and you can see that that ray is going through just half of a rotation, so it's 180 degrees. We need this vocabulary in these first couple slides to understand our protractor postulate coming up. 3 questions here. What can you say about every ray in a half rotation? So every one of these rays, there's something that's true about them. And every real number from 0 to 180, we're going to say something about them. And they're actually going to be the converse idea of each other. Does that give you a little hint? And then what's going to be true about each pair of numbers in a half rotation? So if we were to take this number and this number, what's true about that pair of numbers? Well, let's get into them one at a time. What can you say about every ray in a half rotation? So every ray, the ones pictured and also the ones that are not pictured. Remember, there's an unlimited number of rays. Every ray in a half rotation can be numbered with a real number from 0 to 180 called its coordinate. You don't have to memorize this. It's just the ideas that you have to get straight here. So all it's saying is every ray here has a number, a real number, and it'll start at 0, and then there's a 1 and a 2 and a 4.5 and a 9 and a 10 and so on, all the way over to 180, because it is a half rotation. The converse is also true. Can you figure out what that's going to say? If we just said every ray can get a real number from 0 to 180, the converse is going to be every real number from 0 to 180 corresponds to think is matched with, excuse me, exactly one ray. So here we go. In other words, every one of these rays has a real number from 0 to 180. And every number on this scale from 0 to 180 corresponds with a ray. Okay, that's good. And that's important to get us to this answer to this third question. What can you say about each pair of rays in a half rotation? So if I take this ray at 40 and this ray at 70, there's a pair of rays. Think about what we did with the ruler postulate. Maybe that'll give you the answer. For every pair of rays, there corresponds exactly one real number called the measure of the angle that the rays determine. I had pointed to 40 and 70. There's one real number that tells the measurement of that angle. That tells us what a protractor does. It measures angles. Kind of a complicated way to think about it to get there. Again, all of this is for background. You don't have to memorize any of this. In his old book, he used to have you do that. So for every pair of rays, if I take an 80 and a 120 here, there is exactly one real number called the measure of the angle. So 80 to 120, well, that would be 40. So here we finally get now to our postulate and our theorem and our definition. This you memorize. Similar to the ruler postulate, the rays in a half rotation can be numbered from 0 to 180 such that positive number differences measure angles. There's some difference, right? The ruler postulate said the points on a line can be numbered such that positive number differences measure, so this whole line is the same, but it measures distances. Here we have the rays in a half rotation can be numbered from 0 to 180 such that positive number differences measure angles this time. So here's just a demo of that. They've chosen this pair of rays, 160 and 60, and positive number differences measure the angle. So that angle AOB is 100 degrees. Since there are two scales there, it doesn't really matter which scale you've decided to use. The difference from 120 to 20 is also 100. Here we see it again. Two other angles, COD. Just each ray has a coordinate. There it is. There it is. And positive number differences measure the angle. So here's our protractor postulate again. You can see it. Memorize that. The rays in a half rotation can be numbered from 0 to 180 so that positive number differences measure angles. Protractor postulate. Similar to the ruler postulate. Few definitions. I don't think these are going to be new for you. Keeping them straight maybe is a little. Acute, less than 90. And unfortunately in today's society, oh, that's a cute little thing. Acute, it's the one that's less than 90. It's smaller. For some reason people think small is cute. Right angle, if and only if it is 90 degrees. Obtuse, it's obtuse. It's more than 90. But it's got to be less than 180. We call it something else when it's more than 180. We call that a reflex angle. I believe we've mentioned that before. Straight angle, if and only if it is 180. So realize they all start this way. An angle is, and then there are four choices there. Get those into your head. Now we need to define, how do we know if a ray is between two others? And if you make the connection between how do we know a point is between two others, this is going to be pretty easy for you. How do we know that ray OB is between ray OA and ray OC? Well, it just looks like it. Well, that's not good enough. Start with some vocab again. We've got coordinates. Those are normally going to be numbers. And we have the rays OA, OB, and OC. So here's the definition. A ray is between two other rays in the same half rotation if and only if, so that's the definition, its coordinate is between their coordinates. Then they have the brief form, which some of you may want to use in a quiz. When you see this, OB is between OA and OC, just as you see in the picture down here. Either this is going to happen, A is less than B is less than C, or A is greater than B is greater than C. Just depends on how it's laid out. In this particular arrangement of rays, because A is greater than B, which is greater than C, we know that ray IT is between rays IF and IS. Looks like that. And we can say that's true because its coordinate is between their coordinates, as you can see here. If we were to put the IS on this side and the IF over here, then we would need to change this and say because 20 is less than 90, which is less than 135. That gets us then to our second theorem this year, Betweenness of rays theorem. Again, hopefully you can see how similar it is to the betweenness of points. Betweenness of points, we said if one point is between the other two, then the sum of the two segments equal the whole segment. Here we say if ray OB is between ray OA and OC, in other words, we've already determined that. This is our given. It is between. Then we can, let's put some coordinates to that, then we can say that angle FIT in this case, which is 45, how did I get that? Did I just put that in? Positive number differences measure angles, plus angle TIF, which would be how many degrees? TIS would be how many degrees? Positive number differences measure angles, 70 degrees. And how would that end? Well, look up here. This angle plus that angle equal whole angle. Angle FIS equals, and this is the betweenness of rays theorem. It's the sum of these two angles. Hopefully you can do that one in your head, or 115 degrees. Betweenness of rays theorem. Here's the proof to it. There is an assignment 1 problem that does this same proof, but it does the case where A is greater or less than B, which is less than C. So pay attention to this one. This one will help you in the problem sets. Where are we getting OB is between OA and OC? Getting the hang of this now. Usually there's going to be a given at the beginning. So it's between. And they say hypothesis. I prefer that you use the word given in there. The next step, because it's between, because OB is between OA and OC, we know something about the coordinates. Well, it was given right here, that A must be greater than B greater than C, so that's betweenness of rays, coordinate is between, and this particular case where A is the largest. Moving on. Looks like we're trying to give the measure of angle AOB right here, AOB. What would allow us to say that that's equal to A minus B, looking at the coordinates A minus B. The same thing with the other angle BOC. Have that one? That would be the protractor postulate. Positive number differences, there they are, differences measure angles. This one was a little tricky on the betweenness of points theorem, but if this angle is equal to that expression and this angle is equal to that expression, we've got equals, and we're going to add them to equals. So angle AOB plus BOC equals angle A minus B plus angle B minus C. So that would simply be addition. And then we simplified just a bit, because we said minus B plus B goes away and we're left with angle or A minus C, which is kind of interesting. A minus C, hopefully you see why. We can say that angle AOC is A minus C, again the coordinates A minus C, and that would be our new ruler postulate. Positive number differences measure angles. And they think we can go right to what we're trying to prove up here on the top at this step already, and we can. Why? Well, I'll notice on the left side I have AOB plus BOC, which was right here. But the right side is different. I have angle AOC, and up here I had A minus C. Did you notice in step 5, though, that angle AOC is equal to A minus C? So if two things are equal, we can, yes, substitute. So I'm going to take angle AOC and substitute it in for A minus C. And we end up with our proof. And that then is substitution. And here's, you see, we use steps 4 and 5. We started with 4 and we substituted in 5. All right, so here we go with a problem set. Going to be real similar to the one of the previous lesson. Stating these sentences. He needs you to have these in your head, get them memorized. 3 rays and a half rotation. You can see them up there, have the following coordinates. Try to put the letters in there before I put mine up there. There are 2 questions about it. Which ray would be between the other 2? Hopefully you know all you need to do is take a look at the coordinates and figure that out. Then name and find the measures. What you're going to need to do is use the ideas we had from this lesson, Betweenness of rays theorem and the protractor postulate. There's a little hint for you. Why did I do that? Well, I saw that HO was 180 degrees, so where is the 180 going to go? And then 1 is a much smaller coordinate, so it looks like it starts at 0 here and runs around to 180 because HO was 180. So you could put the other 2 in there, and that should help you pass this one. An old geometry book, very old geometry book, that definition, if you make any 2 half lines, AB and AC, from a point A, they are said to form an angle. Picture down here. The point A is called the vertex. AB and AC are called the arms of the angle, so a little bit different vocab than we use. We name this angle BAC, putting in the middle the name of the vertex. That's what we do. And on each side of this, the name of a point on one of the arms. If P is another point on the half line AB and Q is another point on half line AC, the angle PAQ is only another name for the same angle. So now some questions. What do we call the half lines that they use up here? What do we call the arms of an angle that we use up there? And pick the right name. Pause if you need more time. Navigation is used a lot, it says, and these are signal lights warning sailors of dangerous areas in the sea. You can see some stuff there that I guess would cause a problem. The figure at the right shows a red sector, dangerous area. Some questions. What are the numbers 45 and 120 called with respect to the sides of the angle opposite the danger angle? So here's the danger angle. Here's the angle opposite that danger angle. What do you call these numbers? What's the measure of this angle? You're using the protractor postulate. What kind of angle is it? You're using the definitions that you had. Here's that other angle I was talking about earlier. Although angles in geometry have measures of no more than 180 degrees, the number of degrees through which something can turn is unlimited. 2 examples from sports are listed below. If you want to try the links, they're kind of cool. So answer those 2 questions. This one sometimes boggles people, slows them down a little bit. We've got a plank, a board that you'd build with. In 2 dimensions, you just flatten it out. We've got some angles in here that they're going to ask you about. DCF and so on, all those angles. If it were a real board in 3 dimensions, it would certainly look different. So they ask you some questions about that, keeping that in mind. There's just a little bit bigger view of it in case you need it. Birds and planes sometimes form angles in the sky. There's a reason for that. It kind of reduces the resistance. the leader here has the toughest time. Kind of the same with biking, but not V's. The photograph shows geese flying in a V formation. Is it possible to tell from the photograph what type of angle the birds are flying in? An acute angle or an obtuse angle? Can you tell from the picture as opposed to, for instance, just standing underneath it and looking? So answer that question. At the same time, there is a fact about this. Do you know why one line of this V is always longer than the other one? There's a good reason for that. If you know, great. If you don't, you can ask me. Bubble angles. So we've got them rearranged. Bubbles, have you ever seen that in a sink? You make some bubbles and they'll kind of bump into each other, jump into each other, and then they make some figures like this, little diagram. So some questions about that. Again, he's working on the definitions of the different angles. As he is in this cactus spoke one, find the measure of one of the angles formed by the two spokes. So, for instance, an angle right in here. Find the measure of that angle. How are you going to do that? Well, the given, they're evenly spaced all around the center, so might have to do some counting there. Here's drawn a diagram of that with some coordinates written in there. So right now we're going to ask you to work with that protractor postulate and betweenness of rays. So a few questions about that. Measuring some angles. So we're looking at the betweenness of rays theorem. Runways. So here's a runway that's pointing north, and here's a runway pointing east. Looks like they want to save on paint on their runway or something, because if north is 0, east wouldn't be 9, but it would be 90. So there are a few questions about this. What do you think the number would be, this one pointing south and the one pointing west? How are they related to numbers on a protractor, circular protractor? So once you think about that, talk about that, get an answer down. Airplanes sometimes take off from either end of a runway depending on conditions. If one end of the runway is numbered 5, what do you think the opposite end is numbered? Keep number 36 in mind, and these labels they have on the existing runways. So if he's taking off at 5, it's not really 5, what is it? And then the runway you got to assume is straight. What would be the other end? What would be the label there? Two runways are pictured here. Here's 25L and 25R. What does this numbering indicate about their directions? 25 says something. What angle do these runways make with due north? Sounds a little confusing to me, I thought. So let's see. If I put a runway here, north, I don't know why it does that little thing. Forget that. And then the other one is 25. Remember what answer to 36 was? So it's probably more like 250. Okay. Can I erase those other ones that are in the way? Let's see. It takes more than just what I want. Alright, so there's north. This one's 0, we had from earlier. And this one they're calling 25. What angle do they make with due north? What do the letters represent in the photograph? Probably gave you too much there, but that's okay. Pool table. There's a little bit of physics involved here. When a pool ball banks off a cushion, the angles that its path forms are equal. So what they're telling you is that when you shoot a ball from A to bounce at B or P off to B, this angle 1 would be the same measure as angle 2. Same thing if you put C, if you bounce the ball from B up to D here, then CPX would be the same as DPY. It's just a physics law. So with that in mind, answer some questions using the properties that we learned today. The protractor postulate, the definition of betweenness of rays, and the betweenness of rays theorem. I think I just repeated this slide. I'm not exactly sure why. You young enough to recognize this? The NBC peacock. It's got 11 feathers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. How many degrees would each angle have if the peacock had 9 feathers? Remember what these feathers are arranged in from earlier in the lesson. I'd call it a half rotation. It should give you enough to work your way through these. Answer to 47 isn't a nice, clean, satisfying, simple answer, but you can get it. Minutes and seconds. Units of angle measure smaller than a degree are the minute and the second. So when you're measuring an angle, we had a problem earlier than this. If you're at 1 degree, that is not the smallest angle possible. You can break it up into minutes and seconds. What unit besides a degree also is equal to 60 minutes, with a minute being 60 seconds? How many seconds are there in 1 degree? And a few more questions about this. The Earth rotates on its axis in 24 hours, a little bit of a hint to a previous answer. How many degrees are in 1 rotation? And it goes all the way around. Through how many degrees does each turn in 1 hour? So there's a little algebra going on here. Not sure why I put that picture there, but I did. But that's what they're talking about as it turns around. Promised this from earlier. We proved this, the betweenness of rays theorem. He's saying follow that guide to prove it for that case. And finally, a set 3 problem. Kind of interesting one. Geometrical puzzle in the Washington Post attracted more attention than its author could have imagined. Here's what the author says. The UPS, which had carried the quiz in which the puzzle first appeared, insisted it could be solved, but by a method too long to print. The man who set the puzzle said that he had forgotten how to do it and could not repeat his lost performance. He had recourse to 3 dozen geometers, none of whom, he said, could find a solution. Coming up, the picture here. The problem was to find the measure of EFB in the figure at the right without measuring or using any advanced math. So use a ruler and a protractor to make an accurate drawing. Make it as large as you can. And then the idea is to figure out some of the angles. Which angles can you calculate and write their measurement down? And then obviously it couldn't be that easy an answer. You had geometers and a whole bunch of people trying it. But if your drawing is reasonably accurate, you should be able to make a pretty good guess at it. What do you think it is? So here's the drawing. Okay, they're wondering about this angle up here, I think it is. Or no, which one is it? Angle EFB. EFB. So this one with the question mark. So figure out which ones you can calculate and see if you can get an estimate at that angle right there. All right, that's it then. Work these through. Come with questions. Always willing to help, obviously.